this video, we'll be talking about section 6.1, which is solving one-step inequalities. To start, we have some vocabulary here. We have an inequality is a mathematical sentence that contains the symbol less than, greater than, less than or equal to, greater than or equal to, or not equal to. Second vocab word here is when solving inequalities, you can write the solution set in a more concise way using what's called set builder notation. For example, this right here is the example of set builder notation. That is read as the set of all numbers such that x is greater than or equal to -4. This bar right here is what such that means. Sorry, the bar represents such that. So you'd be saying x such that x is greater than or equal to -4. Here's what I will tell you. In Algebra 1, we really don't use anything with set builder notation. So this is just kind of to expose you to it. Hopefully make it seem somewhat familiar. When you get to your upper level math classes, that's when that will heavily come into play. So with that being said, we're going to go ahead and move on down here to our set of examples. We have graphing inequalities. So looking at number 1, they want us to graph x is less than or equal to 4. Now, I will also remind you, the best tip I have for remembering which one's which, what I mean by that is like which one's less than, which one's greater than. Less than looks like a squished L. And then greater than would obviously be the opposite of that one. So that's kind of how I always remember which one's which is the one that looks like an L is less than. So on number 1, x is less than or equal to 4. Here's what we need to start with. We need to start with our graph because right now it's blank and we need to figure out what to put on there. So here's my expectation. We start with the number in the middle and that will always be the number that we're talking about in the problem. So in this case, 4 is going to be in the middle. And then my expectation is that we have one number higher than 4, which is 5, and then one number lower than 4, which is 3. So you're always going to have 3 numbers on your graph in consecutive order from least to greatest. So we have 3, 4, and 5. Now we need to actually put x being less than or equal to 4 on the graph. So we're going to start with an open circle here, or just a circle. Now, an open circle would mean that 4 is not included. However, if x is less than or equal to, this bar right here means or equal to 4, that means 4 could actually be an answer. So we're actually going to close that circle because 4 is included in the possible answers that there are for number 1. So if I plug 4 in for x, and I say 4 is less than or equal to 4, that would be a true statement because 4 is equal to 4. So then 4 is included, but then we also have an entire range of answers here. So then if we have x is less than 4, I always ask myself, is 3 less than 4 or is 5 less than 4? Well, in this case, the 3 would be less than 4. So then we shade in the direction of 3, aka where all of the numbers are smaller and smaller and smaller. So this whole purple shaded area would be answers that would satisfy this problem. So a couple things to note here. I will show you multiple ways of graphing. You can pick the one that makes the most sense to you, the one you like the best, whatever it is. But the biggest thing I need you guys to all pay attention to is we do have an arrow at the end of our shading. You do have to have your own arrow. This black arrow right here is not sufficient enough. You need to have your own arrow to show me that the shading goes forever and ever. So then moving on here to number 2, starting with our number that we're actually talking about being -2. One number higher than that would be -1. One number lower than that would be -3. Please make sure with the negatives you pay very close attention. These number lines often get messed up because of the negatives. It throws people off. So then we would go on to start graphing here. We would have an open circle at -2. It's going to be open in this case because it's just greater than. There is no or equal to. So -2 is not included. If I was to plug -2 in and we said -2 is greater than -2, that would not be a true statement. This would not count. So -2 is not included. But then where are all of the numbers greater than -2? Well, that would be all of the numbers to the right. So then some people like to just do a line like this for their shading. I'm totally okay with that. Again, you just have to have something that shows your shading and then an arrow at the end of your graph. So then looking at number 3 here, we do have a little bit of a problem. So I don't know if in years past, teachers have told you to pay attention to what arrow, like what direction the inequality is pointing. So like on number 1, it's pointing to the left. So we shaded to the left. On number 2, the inequality is pointing to the right. So we shaded to the right. That does work, except for only when x is first. So what I mean by that is if it comes first, then technically that rule does work. If it comes first here, technically that rule does work. In this case, X is not first. So just because this is pointing to the left does not mean we shade to the left. So what I actually want you to get in the habit of doing, because graphing with X first is much, much easier to understand than graphing when X is not on the left. Because if -7 is less than X, that's a little bit harder to kind of wrap our brains around what is being said here. So if I switch this around and I put X first and then I put the -7, we have to be very careful about what our inequality says here. If the inequality right here is opened up towards the X, we have to make sure it still is continued to be open towards the X. So then that means my inequality sign would actually flip here. So now I'm going to graph X being greater than or equal to -7. So then I'm going to put -7 in the middle, -6 to the right, -8 to the left. And then we're going to have a closed circle because it's or equal to. So that means -7 is included in that answer. And now that X is first, if X has to be all of the numbers greater than -7, that would mean we would shade to the right. Some people like to do a line straight up and then straight over like this. I'm okay with that kind of shading as well. Again, as long as I can tell what direction you're shading and you have an arrow, it doesn't matter to me. On number 4 here, we're going to put 3 in the middle, 4 on the right, 2 on the left. I will tell you a very, very common mistake that gets made is some people put 3 here, 4 here, and then 5 here. This is always an accident, obviously. I'm very confident in your ability to count in order. However, some people get rushed and they go 3, 4, 5, and it comes second nature to us, right? To continue counting in the direction you're counting. So please make sure you don't do that mistake. It's actually a lot more common than you'd think it is. So make sure you're going slow on your number lines and your number lines make sense. So going back to number 4 here, I would have an open circle at 3 because it's not or equal to. And then if X has to be all of the numbers that are less than 3, that means I would shade to the numbers that are smaller. And actually, we're going to change this. I'm going to go above the graph. This tends to be a pretty popular thing that kids do. So my circle is above the graph at 3, and then shading to the left would look like this. So there's a bunch of different examples of how you can shade. Again, like I said, I don't really care how you show it as long as you have the circle open or closed, you have shading somehow, and you have an arrow at the end of your graph. Now on 5 through 8, we have basically the opposite of what we were just doing. So we have a graph that we have to write the inequality for. So if you paid attention, right, we really, really, really like X to come first. So I know that I have to start with X. That's my shaded area. And then I'm going to start with the number that's on the graph. So I have X and 1. That's where my dot is at 1. Now, the shading is to the right of 1. And if you notice, starting with 1, it shades 2, 3, 4, 5, 6. Those are all bigger than 1. So then that means that my answer has to be X is greater than 1. The last thing to pay attention to is the fact that that's a closed circle. So then this is actually X is greater than or equal to 1. So then looking at number 6, again, starting with X and the number that the dot is at, which would be -6. Your shaded area goes to the left of -6 or shades all of the numbers smaller than -6. So then this would be less than. It is an open circle, so it would just be less than. Then we have number 7 here. Again, X and 5, starting with the number that has the dot. This has all of the numbers less than 5 shaded. So then we put less than. Remember, if you can't remember the difference, less than is the one that looks like a squished L. And then this one does have a closed circle, so it would be less than or equal to 5. And then number 8 here, we have X and 0. And this one shaded all of the numbers that are bigger than 0. So this would be greater than. Open circle would mean it would just stay as greater than, no or equal to bar. Now, before we go to the next page, this table just couldn't fit on the next page. So basically, all you need to understand, we are getting ready to talk about adding and subtracting with inequalities. The only thing that this table is really telling you is that whatever you do to one side, you have to also do to the other side. So if you add a number, oops, thought I had a pen here. If you add a number to one side, you got to add the same number to the other side. If you subtract a number from one side, you got to subtract the same number from the other side, which we should know from solving equations. That rule doesn't change. So let's go ahead and go on to page 2. Alrighty, looking at page 2 here, we have 9 through 14, solving inequalities. So we're trying to get X by itself. On number 9, I see X minus 10 is less than 5. So in order to get rid of that minus 10, I need to add 10 to both sides. Remember, we're still doing inverse operations or the opposite. So then I would have X is less than, the one that looks like an L, 15, and that would be our final answer.
Sometimes I may ask you to go ahead and graph that, so you could draw your own number line, or sometimes I'll give you a number line, put your 3 numbers on there, put an open or closed circle, and do your shading. But in this case, it just says to solve, so we're not going to graph any of them. On number 10, I see -9 plus x. I need to move the -9, and I'm going to do that by adding 9 to both sides. So I have x is less than or equal to 25. On number 11, I'm going to subtract 24 from both sides. So then I have x is greater than or equal to, this should be 37. And then on number 12, I see 88 is less than x plus 13. Again, trying to get the x by itself, I'm going to have to undo that plus 13 by subtracting 13 from both sides. This would give me 75 is less than x. I do want you to be in the habit of putting x on the left, because later when we start to graph these, again, like I said, it's going to be much easier to graph them once x is on the left-hand side. It's much easier to read out loud, to comprehend. So we're going to go ahead and make that a habit right now. So if I want to switch around the x and the 75, I have to pay attention to right now that inequality is opening up towards x. So when I flip around x and 75, it still needs to open up towards x. So 75 is less than x is the same thing as x is greater than 75. Looking at 13, this one's a little bit different because I see 2x terms here, so I definitely need to combine them together. But then the question is, which one do we move? So I notice that there's a 3 here on the left-hand side, and there's no constants on the right-hand side. So I'm going to go ahead and leave the 3 on the left, and I'm going to subtract 9x from both sides. So then this would give me 3 is greater than or equal to x. And again, I want to be in the habit of putting x on the left, so I'm going to switch these around. And notice it's opening up towards the 3, so I need it to continue opening up towards the 3. Okay, on 14, very similar to 13, we're going to subtract 7x though from this, or in this case, sorry. So then that would give me x is greater than 6. No need to flip it around because x is already on the left. Okay, and then we have this word problem here. So Luke's wireless contract allows him to use at most 5 gigabytes. So that's actually our first part on this table. Luke can use at most 5 gigabytes. I do want you to go ahead and add another phrase in here. Another way that you could say at most would be no more than. These are going to be the 2 most common things that you say that relate back to the inequalities, because you'll notice it's not he has to use 5 gigabytes. He can use at most 5 gigabytes. So it could be anywhere from 0 to 5 that he uses. There's a whole range of different possibilities that he could use there. So our variable, we're going to let g equal the number of gigabytes that Luke has left to use. And you'll find that from the last sentence here. Complete the table. Oh, wait, I lost my space here. How many gigabytes of data can Luke use during the rest of the month without exceeding the maximum allowance? So that's where I got defining our variable there. So let g equal the number of gigabytes that Luke has left to use. Next, we need to actually write the inequality. This is typically the hardest part, is writing the inequality, especially when the numbers are a lot smaller and we can do a lot of this math in our head. We tend to not want to write an inequality, but the directions say that we do have to write an inequality. So basically, you have to start with how much data Luke has used so far. So he has used 3.7 gigs of data. Now we have to pretend that these numbers are really hard. We can't comprehend the math in our head. So we have to think, he has a certain amount left to use. Now I know a lot of you can do the math in your head and you know what the answer is, but we're going to pretend like we don't know the answer. So 3.7, he has some left that he can still use. So we're going to add however much that is, which is g, or you could use x if you really wanted to, but they told us to use g here. So 3.7 plus g, that would be what Luke can use. And I'm going to leave a space here. His plan says that he can use at most 5 gigabytes. So then we have to fill in the inequality. If it says at most, he can't go over 5 gigabytes. So this part right here, 3.7 plus g, must be less than or equal to 5 because he can't exceed 5 gigabytes. Now that we have our inequality set up, we can go ahead and start solving it. So then we're going to subtract 3.7 from both sides. And that's going to give us g is less than or equal to 1.3. And then don't forget, since it's a word problem, we have to actually answer in words still. So we can say that Luke can use at most 1.3 gigabytes. Now, something I need you to understand is you have to include that at most there in your answer, or you could say no more than. So Luke can use no more than 1.3 gigabytes. That reminds us that there's a range of gigabytes that he can still use. He could use 0, or he could use all the way up to 1.3 more than what he's already used prior to figuring out this problem. He's used the 3.7. So be very specific in your answer there. Let's go ahead and move on to the last page. So this table basically talks about the same thing as the table earlier in the notes. This tells you that whatever you do to one side, you have to do to the other. However, multiplying and dividing is a little bit more special. You'll notice right here, if you multiply by a negative number, the direction of the inequality sign must be reversed or flipped. Same thing for dividing. If you divide by a negative number, the inequality sign must be reversed or flipped. You'll notice over here, if it's a positive number, nothing changes. The inequality sign stays the exact same. So again, just to reiterate, when you're adding or subtracting, if it's adding or subtracting, the sign never, ever, ever flips unless you're flipping around the order of your final answer. That's the only reason you would ever flip your inequality sign. For multiplying and dividing, if you multiply or divide by a negative number, that's when the sign flips. And you're going to see what I'm talking about on 17 through 20 here. So on 17, I have x over 9 is greater than negative 2. I need to multiply both sides by 9 to get rid of this 9 on the bottom. So those cancel out. I have x. I multiplied by a positive 9. So my sign does not flip in this case. It stays as greater than. My answer would be negative 18. So x is greater than negative 18. Now on 18, I see negative 2/5 x. We have to multiply by the reciprocal, so 5 over 2. But then we also have to pay attention to this negative right here. I need that to become a positive x by itself. So I need to multiply by a negative 5/2 because 2 negatives would make a positive. Now in this case, you're multiplying both sides by a negative number. We have to flip the inequality sign. You're going to see that I write flip quite a bit. You can if you would like to, but you definitely don't have to. It's just a good reminder. So my negative 5s cancel out, my 2s cancel out. I'm left with just x. My inequality sign has to flip. So it's no longer less than or equal to. It's got to be greater than or equal to. And then 12 is technically over 1. So 12 times negative 5 would give us negative 60. 1 times 2 is 2. Some of you can do this math in your head, so you could skip that first step there. Of writing negative 60 over 2, and you could just go straight to negative 30. Okay, on 19, we need to divide both sides by negative 3, but notice I'm dividing by a negative. So again, in this case, my sign flips. So I have x is greater than negative 7. And then on 20, 4x is on the right, but I need to divide both sides by 4 because I'm trying to get x by itself. Since you're dividing by a positive number, the sign does not flip, so then it would be 5 is greater than or equal to x. Now, totally separate from multiplying or dividing by a negative, I again like my variable to be on the left, so I'm going to rewrite this as x is less than or equal to 5. But please know that the only reason that sign flipped was because I changed the order of the 5 and the x. Okay, has nothing to do with dividing by a negative because we definitely did not divide by a negative number. Okay, and then the last thing we have here is this word problem. So first things first, always define your variable. Question says, how many pages are there in the novel? So x is going to represent the number of pages. And then Teddy has read approximately a fourth of a novel. Well, if she's read a fourth of a novel, that means she's read a fourth of the number of pages there are. So then I would put 1/4 times x, right? A fourth of the number of pages that she's read. And then it also says that she has read at least 112 pages. So we know that those are equivalent to each other to a point. But notice right here, it says that at least 112 pages have been read. So at least means more than 112 pages. So that would be greater than, and then at least actually means greater than or equal to, because it could be just 112. It doesn't necessarily mean that it has to be more than. So it needs to include that or equal to. But at least definitely means greater than, not less than. Think if you have at least $5, you have more than $5 potentially. So now that we have our inequality set up, we're going to start solving this. I'm going to multiply both sides by the reciprocal, which would be 4, technically 4 over 1, but I'm just going to leave it as a 4 here. So my 4's cancel out. We have x is greater than or equal to 112 times 4 would be 448. And then again, since it's a word problem, we need to answer in words. Now, it's very easy to say Teddy has read 448 pages, but that's not the question they're asking us. The question is, how many pages are there in the novel? So we would say there are, and again, because it's an inequality, we have to be careful. We have to include that inequality in some fashion. So there are at least, and I just stole that from the actual wording right here, but don't forget, you could say there are greater than or equal to 448. It doesn't necessarily make the most sense to say it that way, but it would work. There are at least, though, works perfectly here, 448 pages. And you could put in the novel, but I would be okay if you left it just like this. And that is it for these notes.